Hi, it's Ilya, and today I will continue talking about how to use reinforcement learning to train VLA policies. This is the short video series in which I explain my prize-winning solution in LeHome challenge at ICRA 2026. And in this challenge, I needed to train this bimanual robot to fold different types of garments, both in simulation and in the real life. In the previous video, I already described a lot. What RL algorithm I use, how my whole pipeline of training and data generation works, and then what is the architecture of the policy I'm using. Today, I'll talk about another part of the reinforcement learning training. It's reward engineering and the advantage computation. I will explain different approaches that I tried and then how I combine them together to get the advantage that actually worked in my case. And in the end, we'll talk about inference-time optimization. I will show you how you can improve the results of your policy even after training. I will highly recommend you to watch the first video of this series first because it provides a lot of context for this video. But if you don't want, you still can watch this video separately and you will probably learn a lot of new things. And anyway, I will provide a short few minutes recap with the very concise summary of what I talked about last time. So we are talking about this LeHome Challenge 2026, and in particular in this video as well as in the previous one, we are discussing the simulation challenge and my solution for it. In this simulation challenge, we are provided with some environment in which we need to train the policy to fold different types of garments. You can see some examples here on the screen. And then the success of this folding is defined by positions of different key points. So for example, if we are dealing with this long sleeve tops, then first of all, we need to put kind of sleeves together and we check the distance between these 2 points and it should be below some threshold. And then we need to fold the whole top. And again, we define the success by positions of different points in the end. And for different types of garments, we have slightly different criteria. And we discussed all of them in the previous video. So yeah, if you need some reminder, you can watch the previous video. But for now, you just need to understand how it works in general. My solution is fully open sourced. And again, in the previous video, I already explained how it works on the high level. So I talked about the model architecture, and you need to remember that my model is based on Pi-5 with multiple changes. The most important thing about this architecture to know is that on top of predicting action chunks, I also make some auxiliary predictions. So first of all, I predict success probability and the completion percent given the current images that the policy sees. And we will actively use these values for the advantage computation later. And then if you look to the right, I also predict the delta of the success probability. So given these actions that we predicted, how much we increase the probability of success. And this is one of the things that I use during the inference to make the predicted actions even better. And finally, I have this advantage input to my model. So basically, it means that I can tell my model not just predict any action chunk, but predict the action chunk with high advantage. Or simply predict the action chunk that is, let's say, better than average. And again, advantage computation is a very big part of today's video. And also this advantage input will be used for classifier-free guidance that we'll discuss in the inference optimization part of the video. The next thing that I discussed in the previous video was my overall approach. And again, the reminder that I'm using mix of advantage weighted regression and recap from Pi-6 star. And both of these approaches basically shift the distribution of the actions that we are predicting towards better actions. So towards actions with high advantage. AWR is doing it by simply reweighting, and recap is doing it by conditioning, where we again tell to the model to predict only good actions. But these approaches depend on the definition of advantage. So how do we define, how do we compute advantage? And again, this is the main point of today's video. And finally, last time I discussed the whole architecture of my pipeline. So my pipeline consists of 3 independent parts that are synchronized through the Hugging Face repositories. The first part is training. I use one machine for it, and this machine takes all the available data and train the policy. And also it recomputes advantage every iteration. And again, this is what we'll discuss today. And then we have this right part, the rollout machine or machines. They, again, are running independently. And I will talk about it when I talk about inference optimization, because this rollout collection phase is where inference optimization is also happening. And finally, I have this part with manual iteration and Dagger data collection. And as I mentioned before, I will not talk about it today, but I will talk about it in the last video that will be mostly about the real part of the competition. So this is it that you need to remember from the previous video. Again, if you want more details, you can either read this blog post or read my paper or watch my previous video again. But this is the quick recap of what you need to know. And today we will talk about reward and advantage engineering. Then we will discuss Inference-Time optimization. And finally, we will talk about the results of the whole competition. And we'll have like some discussions and some observations that I had. Now let's move to the main topic of this video. It's reward engineering. But before I start to explain my solution, I want to show you like 1 minute fragment from the previous video that describing some glossary, like in main terms of reinforcement learning that I will be using, because it's very important to speak the same language. So in the beginning, our environment starts from some state. And in this state, we can take different actions. And our policy is something that predicts the distribution of the sections and then somehow samples from this distribution and select the particular action. Then when we move, for example, from state 0 to state 1, we get some reward R0. When we move to state 2, we receive some reward R1 and so on. And then this reward is getting accumulated, and if we sum up discounted rewards, we will get our return. And this is our final kind of target that we are trying to maximize in the reinforcement learning. Then if we just think about all possible trajectories that can go from some state, average them or compute the expected value of the return from them, we will get our value function. If we do the same with one pre-selected action first, we will get Q function. And finally, if you look at the difference between these two values, Q minus V, we'll get advantage. Advantage shows how much the current action is better than the average action in terms of expected return that we will get from the current state. Reward engineering is a very, very important part of the reinforcement learning modeling. Remember that our model is simply shifting the distribution of predictions towards better actions. And reward and eventually advantage is something that defines what is better actions, what is good action, what is bad action. So if your reward is really, really good, and if you really properly predict what actions should be predicted more often, then you will see a very good improvements in your policy using the reinforcement learning approach. If your rewards are not really aligned with quality of the actions that policy is predicting, then your whole approach will converge to something really bad. So let's talk about how we can define this reward, how we can improve it, how we can make it more and more dense and more usable for our model. There are multiple common ways how to define reward or any signal for the model training. Approach number one is simply using the reward that we already have kind of in the simulation. So our simulation has some success criteria, and we define whether we completed the task or not by checking some rules. So let's just use these rules to provide the positive signal for the model training. The second approach is using value prediction. Value function allows us to remove a lot of noise from our prediction, from our reward that we defined somehow else. And it makes our kind of signal much more dense. So we have the actual signal for every step of our process instead of having like some signal somewhere in the end of the rollout. And it helps a lot. Another approach is to look at the completion. So we can train some model that predicts the completion of the task and use it as some reward or some extra guidance for our policy. And then finally, there is this relative success, this GRPO style approach. We simply run a lot of rollouts from the very similar initial states, and then simply compare the results of this rollout. If in some rollouts we solved very hard task, then we should give a lot of advantage to this rollout. If in some rollout we failed in very easy task, then it should be like very big punishment for this rollout, and so on. These are popular approaches, and in my case, I actually used all of them. So I combined all 4 of them into one big advantage formula, and I will go through it step by step and try to explain every decision that I made on the way. First of all, remember how we define success. We have some key points in each garment, and some of these key points should be close to each other in the end. Some of these key points should be far from each other in the end. And if all these conditions are met, we consider the task done. So let's just reuse the same logic, the same exact checks, and give some intermediate reward. Yeah, so we of course can just give reward in the very end, but the problem with this reward is that it will be very sparse. And let's say good actions in the beginning will not get any signal from the reward in the very end. So we want always to make our reward as dense as possible. And again, there is an obvious way how to do it in this case, because we already have this criteria that we check. Specifically, let's look at this long sleeve example. And in this case, the first criteria that usually achieved somewhere in the middle of the rollout is when we move 2 sleeves together. At the image in the middle, the distance between these 2 key points and the sleeves became lower than threshold. And this is exactly where we can give some partial reward to our policy. So what I did, I assigned 0.5 reward to this event. So whenever 2 sleeves become closer to each other than the threshold that we need for the full success, I give 0.5 points. It already made a lot of improvements, because our kind of reward became 2 times more dense than simple success or failure label of the rollout. But we could make it even more dense. So in this case, what I did, I also looked at the process when these sleeves are becoming closer and closer. And basically, if I know that eventually we connect the sleeves, then for every movement that make these sleeves closer, I give some partial success depending on this distance. In this case, if you look at the second image, we move the right sleeve to the middle, and it's basically the half of this subtask of connecting the sleeves. So I give around half of the score. In this case, it's like 0.33 because it even moved a little bit closer than needed. And then when I started to move the next sleeve, it also gave like some small reward. And then eventually this reward summed up to 0.5. And then the second half of the task is simply folding this whole shirt, gets another 0.5 reward. So there is no other logic to make it more dense. And this is the typical picture of how I assign this reward. So now we have multiple points during the rollout where partial reward is assigned. And you can see some real signal even in the beginning of the task. That is pretty nice and already allows to train the model. Of course, these criteria, they're slightly different for different garment types. So for the short sleeves, it's exactly the same. So the logic is exactly the same. Then for the shorts, I didn't change anything. It's usually very, very short task, just one movement. So there is no reason to add any extra deterministic reward in the middle. So for the shorts, it's just state binary in the very end of the rollout. And then for the long pants, I added few more checks to the success criteria and also give some partial success for like first folding of this pants in a half. And then another half of the reward if we finish the task and succeeded. You can again look in the code and find the exact definitions of how this reward is computed, but the high-level logic is as I described right here. The typical chart for the success episode looks like this, like the one on the left. But what happens if we reach this first checkpoint, if we get 0.5 reward, but then eventually fail? You can make different decisions here. I'm not sure whether the one that I made is correct or not, but what I decided to do is to withdraw all the reward in case of eventual failure. So if you reach checkpoint, if you complete the half of the task, but then failed, I give you some negative reward slowly till the end of the rollout. Why did I do it? Because I believe that it means that you made some mistakes in this period, or maybe you even made some mistakes in the beginning, but it somehow still passed these checks and gave you some partial reward. So I need to subtract some reward to make it smaller. Even for the first part of the task, if you reach the first success but then failed, I would rather give a little bit lower reward, discounted reward, to the actions that we did in the beginning of the rollout. Another very nice property of this approach is that the sum of the rewards, so the total return for the whole rollout, is always 1 or 0. And it corresponds to the success of this rollout. So if we successfully complete episode, then sum of all the rewards will be 1. If you failed episode, then sum of all the rewards will be 0. And it makes some formulas simpler, and we'll discuss it very soon. Okay, nice. We made our reward more dense than it was, and it's already a good progress, but we want to make it even more dense. So we want this reward to change every single step. If we are doing something good at these steps, we want to have some positive reward. If we are not doing anything good, we should have some negative reward, and so on. And this is time to remember what is value function. If you start from some point and sum up all the future rewards till the end of the rollout, we will get what's called return. Usually we also use some gamma factor, discounting factor. I kind of omit it in many formulas because it makes it much simpler and more intuitive when we omit it. And then in the end, I will show you some formulas where I put it back. And value function is nothing but just expected value of this return. So imagine you starting from some point, from some state, and you have some fixed policy. And then you run this policy, let's say, 1,000,000 times from exactly the same state. And then you compute the return for every rollout and then compute the average of these returns. This is exactly your value function. This is the estimation of expected value of the return that you will get from the particular state. And if you know value function, we can estimate advantage. The most direct way to estimate it, called Monte Carlo advantage estimation. And this advantage estimation is simply difference between the return that we had in this particular rollout minus value function at this state. So we're comparing the actual return of the particular trajectory in the particular rollout versus kind of expected return that can happen when we start from this the same state. And you can show that this estimation is unbiased. So the expected value of this estimation exactly equals our advantage because it equals Q minus V. And again, this is just the definition of the advantage. This is a very direct way to estimate the advantage of the next action, given that we know the return and the value function for the state. And as we discussed in the previous video, optimizing advantage is kind of equivalent of optimizing return. So if we maximize advantage, if we maximize the relative goodness of every action, we also improve the policy as a whole. And now let's discuss what do we even get from subtracting this value function from return. Why don't we just optimize return itself? The return that we measure in one particular rollout has some variance. It has this noise. This variance can be decomposed into two parts. Part number one is some variance that depends on the value function. It depends on the goodness of the current state. So imagine you are in a very, very easy state and policy will easily solve it, and then you will get very high return from this state. And there is another case where you are in a very, very bad state and there is almost no chance to resolve it. So then if the policy eventually managed to resolve it, it actually means that policy did something really, really good. So partially this realized return depends on the current state and specifically on how good or how easy is the current state. And then there is the second part is the action choice and the outcome. So how good you behaved in this case, given already the current state. So again, this second part looks more at the relative goodness of your actions rather than on the how lucky you are to just end up in this state. And if we move to the advantage estimation, so if we subtract this value from return, then we completely remove the first part of this variance and we are left only with the second part of the variance. And this is exactly what we want, yes? So we want to optimize our policy. We don't care about things that don't depend on our policy. So we're already at this state, yes? So, and then we need to move from this state. And this is what we care about. And we want to generate as good actions as possible from the particular state. So this is kind of good variance because it shows how different actions that we choose behave. And we want to choose better and better actions over time when we train our model. So this is exactly what is important for us. Moreover, you can show that subtracting value is actually the optimal in terms of minimizing this total variance for all possible baseline functions that we can subtract. Baseline function here means that it's some function that depends only on the state and doesn't depend on the action. Among all the possible functions depending on the state, subtracting value function is the best choice if you want to minimize the total variance of this difference. And this is exactly what makes this choice the right choice in this case. For this estimation, remember we use the whole return. So let's say if you made 1000 steps after the current state, then all these steps impact return. And all these steps will impact the advantage of your first actions that you are predicting. It kind of makes sense because these actions, they depend on the first action that you make, but still it adds so much noise that we want to actually reduce it to. And the approach that is used here, it's called temporal difference. And what it's doing. So imagine that you are in the state 1 and then you make some action and then you end up in the state 2. We can predict value for both state 1 and state 2, and we also know some reward that we got by moving from S1 to S2. We can compare the difference between expected value that we had in state 1 with expected value that we have in state 2 plus the actual reward that we got for moving to state 2. And then this difference will show us whether we did the right choice by taking this step. If this delta is positive, it means that we did something good locally. If this delta is negative, then it means that we did something bad. And this is another way to estimate the advantage, but it's very local. It has much less variance, but it actually has higher bias. So there is an approach that kind of combines them together and kind of converges to some middle ground. In this approach, we consider all the steps till the end of the rollout. And then for every step, we compute this delta. And then we apply discounting factor. So sorry, this time I didn't skip it. It's important here. So we apply a discounting factor for every delta and sum all of them up. So if you do it like this, then we get something in between that can balance between this high variance and high bias. And this is called generalized advantage estimation, and it's a very common way to estimate advantage. In this formula, we have this new parameter lambda. So let's look at what happens when we change this lambda. If lambda equals 0, then our advantage estimation simply equals our first delta. So it's exactly as just one delta for one step from S1 to S2. It has low variance, but can be biased. If we set lambda to 1, then our advantage will be exactly Monte Carlo estimation. It will be exactly our return minus our value function, because all these like summations, they will eventually end up canceling each other and we'll get exactly this formula. This approach is unbiased but noisy. And if we choose some lambda somewhere between 0 and 1, we will get something in between. In my case, I use lambda equals 0.99. That is very close to 1, and gamma 0.999, that is even closer to 1. This is why I really like to remove gamma from most of the formulas, because it's very close to 1 and it just adds a little bit confusion, but not so much transparency and understanding. Okay, so it's time to apply it to our particular case, because we know how to compute return in our case. At any state, if our rollout end up as a success, then we will have total return of 1. It means that the extra return that left is just 1 minus accumulated return so far. In case of failure, the total return will go to 0. It means that in case of failure, our return is simply minus accumulated return so far. And if we put everything into this formula, then we can get the value estimation. So our value function is simply probability of success minus accumulated return so far. So it's like very simple formula. And we already have success probability as the auxiliary prediction of our model. Our policy on top of predicting action chunks predicts success probability. So we can simply reuse this success probability and we will get our value function and it's done. So we don't need to develop anything else. Now let's try to compute this delta. So again, delta is just reward that we just got plus difference in value functions. We know the formula of value function is just the success probability minus accumulated return in both of the states. And then the difference of this accumulated reward between two states is simply the reward that we got between these two states. In this case, it's simply R1. So we can use it to simplify formula even further. And the final formula for delta is simply the difference of success probability. So our delta equals success probability in state 2 minus success probability in state 1. At first, you may think that it's very good. It's like very simple, straightforward formula that is easy to use. But then if you think about it, it's actually a problem because now we don't have our reward at all in this formula. So now our advantage doesn't depend on this reward that we just construct. All this reward that we give for the partial completion, for the sleeves and so on, now it's not even part of the formulas. So this absence of the reward in the final formula looks very, very suspicious, but I will not give you a solution right now. So let's park it for a little bit. Let's call it problem 1. And I will discuss it later after discussing problem 2. And I will show that it's not actually the separate problem. It's more like artifact of the mainstream approach of computing the advantage. Remember why we've chosen value as this baseline that we're subtracting from the return. Yes, because it's minimizing the variance of this difference. But there is a problem. It works only when our value predictions are perfect. But our value predictions are not perfect. They're predicted by our model. And our model makes some mistakes. There is some error. The value that we actually subtracting is not the real value. It's some prediction of the real value that has some extra error. And if you take it into account and try to minimize the variance again, we can show that if our predictions are not perfect, we shouldn't subtract the full value from the return. We should subtract some dumped down value. And this alpha factor that we use for dumping this value can be computed based on the covariance between the return and the value that we're predicting. So I'm arguing that because our prediction of value is not perfect, we shouldn't subtract the whole prediction from the return. We should subtract only the prediction multiplied by alpha, where alpha defined by some kind of covariance or correlation of our prediction with the actual return. It's not a mainstream approach. This is something that I propose in my work, and I believe it's better than subtracting the whole value function predictions. Another note here, so this estimation is not unbiased estimation of advantage anymore. So maybe it's not the best idea to actually call it advantage because it's not exactly advantage anymore, but I call it advantage because it plays the role of advantage later in the rest of the pipeline. And I think it's not a big deal if I call it advantage in this case. So this is the adjusted formula for the Monte Carlo estimation of the advantage that I'm proposing, but we can apply the same logic to the delta. And if you apply the same logic to the delta, it will become different. It's not just a difference of two probabilities anymore. It also includes this reward. And let's look what happens when we change value of alpha. If you set alpha equals to 0, then our delta simply equals our reward. And it makes a lot of sense because alpha equals 0 when covariance between our prediction and what we are kind of trying to predict on average is 0. So it means that our model is terrible. So our value prediction is absolutely unusable. And there is absolutely no reason to subtract some random value from our return. There is no way how it can improve any results for us. So in this case, it means that our delta will converge to just the reward. That makes a lot of sense. We say that our value function is useless, and then our advantage should be just our reward. In the another edge case, when alpha equals 1, it means that prediction is perfect, and our model predicts the real value function. We go back to this difference of two probabilities, and this is exactly what we discussed before. And this is our like problem one. Let's talk about it again. But now we can show that it's not a problem. Yes. So we see here that it's true only when our value predictions are absolutely perfect. So they're absolutely correct. And then if they're absolutely correct, it makes total sense to drop reward. Like, why do we need extra reward in the middle of the completion when we have absolutely perfect value function? And this value function, this like probability prediction already gives us everything that we need. This explains why like this problem number one wasn't a separate problem anymore. It was just an artifact of assuming that our value function predictions are perfect. And finally, if we set alpha to 0.5, we will have kind of both impact of probability prediction and rewards. And again, it makes sense. So we have some prediction of probability of success, or like some value function, and we know that it's not perfect. And then we have some reward that we know that it's grounded to the real environment, so it's always correct, but it may be too sparse. So then we just take and combine both of them with some proportion, and it makes total sense to use both of them. And this formula makes, at least to me, it makes total sense. Important remark here, during the actual competition, I made a logical mistake and I somehow thought that we cannot compute alpha based on the real rollouts. But then, while preparing this video, I looked at these formulas again and realized that there was absolutely nothing that stops us from computing it. So I should have used this dynamic alpha that is always updated and computed based on the actual rollouts. But I didn't use it. In practice, I just used alpha equals 0.5 everywhere. But then again, I double checked it on the historical rollouts, and it turns out to be pretty nice guess, because most of the values of alpha computed based on rollouts are somewhere between 0.4 and 0.8. They can significantly jump between different garment types and so on. But generally speaking, 0.5 was pretty nice guess. So I think it didn't cost me much. But if you want to apply the same logic to your experiments, just compute the actual alpha based on the rollouts, based on the correlation of your predictions and the final return, and it will be much better than guessing what it should be. And now a short off topic. Many people who watch this channel know, but a lot of people actually surprised when I tell them that I don't work in robotics. So my day job is related to machine learning, data science, AI, and all the things, but not for the like real world, not for robots, not for hardware, but more like for online optimizations and different like business applications and so on. And usually there is a follow-up question, how I do it then, so how I manage to do these things in robotics as well. And apart from the fact that I've been doing it as a side project for like 10 years or around it, I usually say that I believe that there are a lot of overlap between different problems in this huge area of machine learning, data science, and AI. And if you look at the robotics, especially in the recent years, like last 3-4 years, a lot of these end-to-end policies and all the things related to them are also part of this field. And there are also a lot of these intersections. And the point is that when you start working with robotics problem, it's robotics problem. But when you go like one abstraction level deeper and like write down some formulas to describe your process, your like robot or whatever you are dealing with, it's not a robotics problem anymore, because this is a mathematical problem. So that there are like some laws, there are some math equations, they're somehow connected, there are some relationship between different things, and it's pure math now. And the nice thing about this is that if there is somewhere, anywhere in the world, there is another process that is described by the same equations, then basically it's the same problem now. And if you know how that problem is solved, then you can solve your problem like very easily, because probably there are like a lot of people who already thought about it in the past. And this type of overlaps, they're like everywhere in everything related to machine learning. If you go a little bit deeper, everything is the same. And this is why for me, it's usually very easy to go to these new robotics algorithms and so on, because when I look a little bit deeper, I see a lot of very, very familiar things there. And the idea with alpha didn't come to me like from nowhere. I got inspired by the way how a lot of A/B tests, so online experiments, run nowadays. And there is like a very popular approach that everybody in the industry using. It's called Cupid. And this approach, mathematically, solving exactly the same problem as this subtraction of the value function from your return. Let's look at it in a bit more details. It's not about robotics, but I just want to show you how I usually think about problems like this and what's my thought process and how I find some similarities between different areas in the same field. So yeah, let's look at it, and probably it will help you to get inspiration for your ideas in the future. So let's look at how this Cupid that inspired me works. Imagine that you're running some A/B test. I don't know, you have a website and you change some banner or some button or some logic or whatever, and you have 50% of traffic going to your old logic or old website, another 50% of traffic going to the new logic. And you want to maximize some metric, I don't know, some conversions or something that you want. And then you simply compare the value of this metric on A side and B side of your experiment, and you compute this delta. The problem is this delta is very noisy because there are different customers. Even so, you splitting them randomly, there are always some differences between these two cohorts. And overall, there are a lot of noise in any metric that you are measuring. And the obvious thing that you want to do is to reduce this noise and reduce this variance. And one very widely used approach to do it is called Cupid. And in this approach, what you do, you take the features before experiment started that are not impacted by the experiment and make the prediction of the future value of the metric that you care about using these features. And then you subtract this prediction from the actual value that you see during the experiment. But you don't fully subtract it. So if you fully subtract, there will be some diff of diff comparison and so on. You subtract it multiplied by some factor theta. And this theta is computed using exactly the same formula as the one that I use for alpha. And then you use these adjusted metrics to compare them and to compute the difference between them. And as it's shown on this chart, the variance of these values are much, much smaller than the original values that you would measure without this approach. And this is very widely known and practically used approach. The one that I actually explained in kind of adjusted version of it that I think more common in industry right now. The original approach presented in the paper was slightly different, but I think it's quickly evolved in what I'm describing right now. And this is how, at least in my experience and most of the time in industry, it's used. And it's very, very, very similar to what we are trying to do with disadvantage computation. Let's just compare it quickly. So on the A/B testing side, you have this metric that we want to maximize. On the reinforcement learning side, you have this return that you want to maximize. And then you compute metric prediction on the left side, and you compute value prediction on the right side. In both cases, what you predict is expected value of your original metric that you want to maximize. And then you want to compute this adjusted version of the metric that is minimizing the variance, but still leads you to the same decision in the end. And in case of Cupid, you know the solution. So this solution is known. I used it many times when I was running A/B tests. And I know that there should be this theta factor that is dumping our prediction. And when I looked at the reinforcement learning case, I've seen exactly the same mathematical problem. But for some reason, people don't apply any coefficient there and just subtract the whole prediction. And I thought that, oh, something is probably off. I tried to write down all these formulas and realized that it actually should be the case. So we should also dampen this prediction depending on how good our predictions are. And actually, this is the same mathematical problem, so it should have the same mathematical solution. And honestly, I'm a bit surprised that it's not done in reinforcement learning. After the competition, I did some mini research and tried to find other any mainstream papers where it's proposed. And I didn't find anything. So there are some discussions that probably subtracting the whole value is not the best idea, but everybody still keep using it. And I didn't see any paper that is doing exactly what I'm proposing to do here. It's pretty surprising because, again, this formula from the Cupid, it's also not something new, and it's used in many other areas. It's basically just a linear regression formula, to be honest. I'm still a bit confused. I don't know whether I just found something really new or I just made some logical mistake and presenting you something very weird. So if you know anything about it, if you ever seen a paper that is using something similar, or you believe that you know that it's incorrect and you can prove it, please leave a comment and let me know. I would be very interested to learn more about it and discuss this approach. And now let's go back to robotics and reinforcement learning, and let's talk about gamma. Again, I removed it from most of the formulas, but let's just add it back and show that we still can have formulas with gamma. If we simply add gamma back and repeat all the steps that we did before without removing it, then we will get this formula that it's a bit more complicated. But again, remember that this gamma is very close to 1, so it doesn't really introduce a lot of differences. So you as well can just use 1 as a gamma, and I think it will work fine. But this is the final full formula. And if you really implement this approach, there is no cost of using this full formula. So I just use the full one. All the intuition behind it kind of stays the same. It was just much easier to explain it without gamma. Now let's go back to this picture. Remember, so we have this densified reward now. And also we have value prediction that make it even more dense. So what can go wrong? The problem is that when we have very, very high success probability, our success predictions saturate. And they go very close to 1. And we completely lose the signal. So we have some signal around the actual points where we get reward, but it's not really what we want because it's not properly distributed to the rest. And this success probability just stays near 1. So eventually it negatively impacts the training process for the easy garments, so I don't like it. This is why I decided to add another signal that is guiding our policy training. I added this completion prediction that also predicted from the kind of same data using the same actual input vector as a success probability. But instead of predicting success, it predicts the completion % of the task, given that we will actually successfully complete the task in that. You can see that this prediction is actually pretty nice and smooth, and it's aligned with our dense reward. And the nice thing about it that it's always increasing. So even if success probability is very close to 100, you still will get some positive signal for just moving towards the success, moving towards the final solution. So in practice, I do it through this potential shaping. So I define this potential as a completion prediction multiplied by another alpha. So this is not the same alpha, but in practice it's also equal to 0.5. So eventually I just, again, compare the completion prediction in the current state and the next state, compute the difference between them, and then multiply by this damping factor. This damping factor is completely decided by me, so I don't have any way to properly compute it. In practice, you probably, if you have time and resources, you should optimize it. But for me, I just tried a few different values, trained the model for a little bit, and decided to stay around 0.5. And the final implementation that I use is slightly different from the more classic potential shaping approach, but overall, this is also a common way to adjust your advantage estimation or adjust your reward to get some extra signal to add to your policy training. And now let's talk about another problem. Remember, we have our policy, and our policy is its own value function, so it predicts the probability of success from the same model. And there are a few questions that define how we use it in practice. Question 1, should we keep training this value prediction together with policy? If we don't do it, then it's a problem. Yeah? So if you train it for a little bit and then freeze these predictions, then eventually our value prediction will drift from the policy is changing, value prediction cannot be even completely separated, it just at some point will become kind of messy, whatever it predicts. So it's not even an option in our case. So we need to keep training this value function all the time together with training the main policy. And then the question is, should we repredict all rollouts? So let's say we make a prediction for rollout, and then we keep training our model. And then we, again, want to reuse this rollout for the training because we have this off-policy or offline approach for model training. The question is, should we make these value predictions again? If we say yes and do it every iteration, then we need to ask ourselves what data was actually used for this value training. If we use the same data as we used for the policy training, then the results will be very biased, because it means that we make kind of prediction of the model on the data that was used for training. So we make the predictions on the training data, and the policy, like any machine learning model, overfits on training data when we train it. So it will be very biased, and it will not really represent the good value function predictions anymore. If we train it on the separate holdout, then we kind of waste these resources. Yeah, so these rollouts are pretty expensive and we need to collect a lot of them. So if you have separate holdout for the value prediction, it's kind of nice and it will work, but it's just expensive for us. So we probably shouldn't do it. So the decision that I eventually taken is to make the prediction only once at the collection. So whenever we collect the rollout, we also make the prediction of the value function, and we save it forever. Our success probability prediction stays there forever. By design, it has a problem that it's becoming stale. Yes, so our policy evolves, so our success probability should go up for the same states, but we never update it. So it's the problem. But on the positive side, again, we avoided all the things that I already discussed, and we also save a lot of time on predictions. Yes, so we don't need to load this rollout, load this data, make the predictions of the model again and again. We just do it once, and we anyway predict actions, so it costs us almost nothing. And then we save it for free. But the main problem is that it stays stale. So our value predictions just becoming a bit too old over time, and they are less and less reliable the more we moving forward. To solve it, I need to kind of balance our advantage that is based on these stale value predictions with something that actually never stales and depends only on the objective factors. And here I use this relative success advantage estimation. It's again GRPO style estimation. So I use the garments as groups. So let's say I have some particular garment, some particular t-shirt, and then I run many rollouts for this t-shirt. I know the success probability of this t-shirt. And what I'm doing, I basically give the positive advantage that is equal 1 minus success probability for the successful episodes. And it will be 0 minus success probability, that's negative advantage, for the failed episodes. It's very sparse advantage. It's not nice. It's distributed through the whole episode. So it's not very cool, but at least it's objective. And success probability is changing while the policy keep training, but the actual success of every rollout stays the same. So I decided to kind of keep it as some kind of anchor to kind of counterweight these stale advantages based on the value function. In practice, it's a little bit more dense than just one value for the whole rollout. I use separate values for the first part of rollout, before the first checkpoint and after the first checkpoint. Again, you can find the details in the code, but I don't think it's so important to discuss it here. And then I apply it using some exponentially decaying weight. When I just collected rollouts and has very recent this value or success probability predictions, I rely on these predictions, and I rely on this advantage, and this segment level relative advantage is almost not used. But then over time, when this data set is aging more and more, I replace this advantage with this flat relative advantage. So in the end, the very old rollouts, they have pretty flat advantage. They have some positive advantage for success, negative for the failures. At some point, when it becomes very old, I completely drop it from the training. But until it, I'm just trying to flatten the curve and dump some very high or very low advantages towards some average that depending on the success probability only. And finally, this is the formula that I use in the end. So I combined all these factors together that we already discussed. So first of all, I use this generalized advantage estimation that is based on checkpoints and success probability. Then I have this relative success advantage, and they always summed up with some weights together. And then finally, I have this completion potential that additionally shaping the signal and gives some positive signal for completing the task, even if the success probability was always high for this task. And this is the advantage that I'm using. Again, without ablation, it's very hard to say which of these things are important, which are not. I try to add extra complexity only when I actually face some problems, and at least qualitatively, I've seen that these problems were resolved after these changes. So I believe that I made a lot of good steps, but I also believe that it's not the optimal setup. So I think that there are ways probably to make it better by using the more or less same components that I used. And again, for very, very deep implementation details, you can always look at my code. It's completely open sourced, and there are a lot of very, very small features that you need to take into account when you try to reproduce it. On the practical side, I also show all these advantage components as overlay of the video of rollouts, and it really helps to debug issues. This is it about reward and advantage engineering, and the next big part, the final part of my solution, is inference-time optimization. So when you already trained your model and the weights of your policy are fixed, you still can optimize it and make it work better. There are a lot of parameters that can influence how exactly your model works in practice, and these parameters are not part of the training and they can be optimized afterwards. So let's talk about the parameters that I have in my model and how exactly I optimize them. First of all, there is some post-processing that we can apply to the action chunk that our model predicts. And I took most of this logic directly from our winning solution of behavior challenge last year. My policy predicts chunk of 30 actions, but it doesn't mean that we need to execute all of them. We can simply execute only first n steps and then predict the next chunk. After we decided how many actions we are going to execute, we can actually speed up or slow down this execution. So we can scale, let's say in this case, this 20 actions up to 30 steps, or squeeze them to 10 steps. In this case, we will execute the same trajectory slower or faster. Okay, so let's say we executed 20 actions and then we make the next prediction, the next chunk. The problem is that originally these chunks are independent. So our policy can predict something completely different that has some jump or that goes to different direction, to different mode and so on. And to fix it, I use inpainting logic. It's kind of my modification of real-time action chunking, and it allows to keep all the action chunk predicted by the model consistent. So they start from the same point and they move more or less in the same direction. And there are a couple of parameters that can be adjusted here. The first parameter regulates how many actions are strictly inpainted. So after we executed 20 actions from the first chunk, we take next n actions that were not executed, and the first n actions of the second chunk are inpainted to be very, very similar to them. The rest of the steps are also guided through some correlation structure, but they're not so strictly inpainted. So there is like much more freedom that model can use when it's predicting the rest of the chunk. And finally, we can adjust how strict this inpainting and guidance is, how much model can deviate from these anchor actions and how much it can deviate from this guidance. In my case, it's defined by how many flow matching steps are actually using inpainting and how many steps in the end of flow matching process are completely free. So here in total, we have 4 different parameters that regulate how we process the predicted action chunk. The next inference-time optimization trick is classifier-free guidance. A reminder that we use flow matching. It means that our model makes predictions in some latent space, and these predictions are not final actions. It's more like some vector fields, some velocities that allow us to transform the original noise distribution into our target actions distribution. And also our model has 2 modes of prediction. In the first unconditional mode, it makes normal prediction. In the conditional mode, we kind of ask model to make only good predictions. So the vector field that is predicted using this conditional mode will be kind of shifted towards better actions on average. And we can utilize it by shifting this distribution even more towards good actions. And it's very simple. So let's take 2 vectors that predicted using the same inputs. One is conditional, one is unconditional. Then the difference between these 2 vectors is nothing but direction towards improving the actions, kind of. So if you move from unconditional vector to conditional, the eventual actions that we generate with this flow are better. So what we can do is simply keep moving in the same direction. Surprisingly, we can move very, very far into this direction, and the resulting vector will still generate a reasonable velocity field, and this velocity field will produce actions that are even better than what we generate using our conditional paths of our policy. I took this idea from physical intelligence. They use it in Pio 6 and Pio 7. But it's kind of nice trick. It's also often used in the image generations when we need to enforce following our prompt or the conditions that we set. And to make it work, so first of all, you need to deal with some latent space. Of course, if you apply the same logic to the final action space, then you simply will go out of distribution. So all your joints will move to some very weird angles and it will not work. And the second, you need to use something similar to diffusion or flow matching because it helps a little bit with some self-healing. So if at some diffusion step you went too far, your predictions are like very, very far and you went out of distribution, then probably next correction step will be very similar in conditional and unconditional modes, and it will push you back to the normal distribution of your prediction. So it's fixing some small issues if your classifier-free guidance is very aggressive. But generally, it's very nice trick, and it's converged to these pretty high values, and really helped in my solution. The next parameter is related to how our flow matching policy make predictions. So the reminder that we take some observations, then they go through the VLM backbone, and at this step, everything is deterministic. So if you send the same predictions to the same backbone multiple times, you'll always get the same predictions. But then when we start using action expert, it's actually becoming stochastic because on top of these keys and values from VLM part, we add some random noise as an input. And then denoising this step using the vector field that is predicted by the action expert. And it means that we can generate different trajectories. We can generate different action chunks depending on this random noise that we use as an input for the action expert. But also our model have this extra auxiliary prediction that tells how much the predicted action chunk improves the probability of success. And we can make these predictions during inference time for every trajectory that we predicted. So if we predicted 3 different action chunks, for each of them, we can predict how much it will increase the success probability and choose the one that has the highest increase to actually be executed. Conceptually, it's similar to how Q-learning works or how word models used for the robot actions predictions. And the number of these candidate action chunks that we generate every time is a hyperparameter that we can also optimize. In practice, all these predictions are very noisy, so I don't think that we actually predict the best action chunk, but probably we avoid executing very bad action chunks from time to time, and this is how this logic actually helps in that. And finally, we can also try to generate the good actions in the first place by adjusting the normal distribution that we use as this original noise input for the action expert. So if we reduce the standard deviation of this distribution, then we simply will predict less outliers, and these outliers are usually bad actions, so bad action chunks. So by reducing the temperature of this original noise, we simply reduce probability of predicting bad actions. So in total, I have 7 parameters, and I want to optimize them. For all the possible combinations of these parameters values that are like thousands of them, I need to run enough rollouts of different garment types to see some statistically significant results, to kind of properly ablate it, to properly optimize and find the optimal set of parameters. So this approach called grid search, and it's very inefficient because you really need to spend a lot of time on collecting rollouts with a very, very bad combination of parameters instead of focusing on the good ones. So there are better approaches. So one of them can be just random search. It significantly already improves the results, number of parameters that you usually need. But there are even smarter approaches. For example, there is some Bayesian optimization. Or in my case, I use Thompson sampling with multi-arm bandits, basically, to optimize them. And let me explain how it works and why it is better than running all the possible combinations of all parameters for this task. An important part of Thompson sampling is beta distribution. So let's discuss how it works. Let's say that we want to model the probability of success of some process, let's say some rollout or some experiment. In the beginning, we have no idea what is our success probability. It can be anywhere between 0 and 1. And let's say that our prior estimation is completely uniform. Beta distribution has two parameters, alpha and beta, and if both of them equals 1, this is exactly a uniform distribution. Now let's run our experiment multiple times. Every time when experiment wins, when we have a success, we increment alpha by 1. Every time when experiment loses, we increment beta by 1. You may see that our distribution changes, and actually when we increase number of rollouts, the expected value, the kind of midpoint of this distribution, is moving towards our actual success probability. It's slightly biased because of our original prior assumptions, but eventually it converges very, very close to the actual success probability. And the wider this distribution is, the higher our uncertainty about this probability estimate. And obviously, when we have less rollouts, our uncertainty is high. But when we increase number of rollouts, increase number of data points, the uncertainty is decreasing, and eventually our distribution becomes very, very narrow around the actual success probability. If you want to use this for the optimization of our inference-time parameters, we can apply this multi-armed bandits with Thompson sampling. It means that for every candidate, for every value of the parameter that we are trying to optimize, we model the distribution of the success probability. So for example, in this case, let's look at the guidance scale. And let's say we have 4 different options. All of them start from the same uniform assumption about the success probability distribution. And then every time we run the rollout, we sample random number from each of these distribution and select the one with the highest sample numbers. And then we simply run the rollout with this particular parameter and update the distribution based on the result of this parameter. Eventually, if the success probability for one of the values is high, it will start to converging towards this value. And then if there are some options that have lower expected probability, but they still have a lot of uncertainty, then sometimes they still will win, and we will run rollouts with them and get more and more data. But if you have some option that has very low success probability, then it will quickly lose, and we will never or almost never use this value again. So this approach will focus on the parameters that have either high success probability or high uncertainty, and will not waste any time on the kind of high certainty, low success probability rollouts. And you can see in this simulation example that we eventually get a lot of rollouts with the highest success probability guidance equals 9. And we have a pretty good estimation. So the success rate on average converge to the kind of modeled success rate that I use for this simulation. But by the rest of the options used much less rollout. They didn't waste resources. And yeah, they converged worse, but we don't care about it. We just care about converging to the highest success probability option. And finally, we can apply this logic simultaneously to all parameters that we are trying to optimize. Technically speaking, we need to make assumption about independence of all these parameters, and it's not really true that they're independent. But even without this true independence, it works pretty well, because eventually the combinations of parameters that work well together, they will be run like faster and faster, and the whole approach will converge around this good combinations of parameters. So there can be some like tricky cases when because of some weird dependencies, they will converge to the wrong numbers, but I think in practice everything works pretty nice. So eventually you simply sample values for all the parameters that you try to optimize independently, and you have this distribution for every single value of every single parameter, and then update this beta distribution for every single value every time when this value is used for the actual rollout. And in the end, just select the set of parameters that get the highest predicted probability of success. In practice, I also optimized all these values separately for different garment types, but interestingly, they converge to very similar values everywhere. And very importantly, I got it almost for free because I didn't wait for the very end to run this inference parameter optimization. I ran it during the rollout collection. So whenever I collected rollouts for reinforcement learning, I always changed these parameters using this Thompson sampling. And also this process added a bit of diversity to the rollouts, and I believe it also helped model to learn the best behavior through this extra exploration. Now you know how my policy for the simulation round works. I described in details all the main parts of my solution. You can find even more details if you look into the code or tech report, but some of the details are probably less important. So I think I try to cover the most important part in these two videos. And now let's look at how this policy actually works. What is the actual rollouts and the results of applying this policy to the robot in simulation. And then let's look at the leaderboard and discuss the result of this competition and some final thoughts that I have after participating in this part. Let's look at some rollouts. All of them are real-time without any speed up and completely autonomous. So this is how my policy controls the robot in simulation to complete the task. I will show you some success examples, one example for each garment type. Whenever it doesn't make any mistakes on the way, it's completing the task pretty nicely. Again, you can argue a little bit about definition of success. Sometimes this kind of fault are not perfect, but it is what it is. These are the rules of this simulation. When we meet this checkpoint criteria, then it's considered success. And now let's look at some failures. So you see that it's starting pretty nicely, but then makes the mistake and then cannot recover from this mistake at all. As we discussed before, my approach doesn't really teach model recovery behavior. So if you want to add some recovery behavior, you need to either collect extra data manually for this, and we'll discuss it in the next video. Another approach is to train multitask model. And then eventually, if you have a lot of data, model will learn some extra recovery behavior from different tasks. But again, this is not what happens here. And you can see that whenever you go out of distribution, whenever, I don't know, everything is messed up, in most of the cases, policy cannot fix it. You can find more examples of successful and failed rollouts in my blog post. And also all the code and checkpoints are available, so you can simply run it locally and generate much more rollouts and explore them yourself. Now let's quickly look at the final simulation challenge leaderboard. You can see that I am on the first place and I have a score of almost 80%, and it's more than 6% higher than the next second place solution. This 6% gap is quite a lot, so I believe that a lot of decisions that I made are important. Even so, I didn't do a lot of ablation or a lot of testing. I think, again, I made a lot of good choices during this competition, and this is why I get much higher results than many other teams. And also, I won in, I think, 3 out of 4 garment types. So everywhere except long sleeve tops, I have the best result out of all the teams. And I don't think there is anything specific about this long sleeve tops. I think I can do better. Also, to be honest, when I trained this model, even in the last days right before submission, I've seen some progress and the success rate was increasing. Also, I changed a lot of things in the modeling like during the competition. It's not like I kind of wrote all the code and then just let it run for 2 months. No, like I've been changing a lot of things during the competition, and what I'm presenting in these videos and in my paper is the kind of latest state of the model. But it reached the state like only in the last days of the competition. So I believe that if I run my pipeline a little bit longer, I can even improve these results, because I didn't see the kind of hard stop of success rate. And yeah, so if you want, you can try to run it. You can start from my checkpoint and train it longer and experiment with it. And I think that you can achieve results significantly higher than 80%. if you simply like run it longer, if you play with it, if you try to maybe experiment with different data collection and augmentations and so on. So it's up to you. It's still kind of open for experimentation. I'm just saying that it's definitely not the limit for this task. And now let me share some final thoughts about this competition and my experience participating in it. So first of all, the reminder that I was focused on the competition itself. So I was focused on maximizing the results rather than ablating every single decision that I'm doing. And so the way how I usually approach it is not extremely structured, because I can apply multiple changes simultaneously and just look at some secondary metrics to decide whether I want to keep them or not, because otherwise it will take too much time to optimize everything one by one. But again, I won the first round, so I believe that I actually made a lot of good decisions. And even if something that I discussed here is not as good as it seems, most of the things are probably correct. So what I kind of really liked and what I would use next time when I need to solve the same or similar problem. So first of all, I like the overall approach. So I think it makes total sense to use something like this advantage weighted regression and recap for this type of VLA policy training. Second, I like how I constructed this reward and advantage. I'm pretty sure it's not the optimal way. I'm pretty sure there are like some mistakes maybe, and I can actually improve the way how it's working. But I believe that all the components that I described are very important. And if you use these components and experiment a little bit, then you can find a very, very good setup that really allows you to train your policy for many different problems. Another big thing is what I discussed in the previous video is how I organize the whole pipeline when everything works asynchronously. So I have completely separate parts for training, for data collection, for automated rollout collection, and so on. And I can scale them independently. I can tweak them independently. So I can, experiment with model while my rollouts being collected, or vice versa. So I think it's very, very good and practical idea. It may be not very good for online reinforcement learning, but anyway, online reinforcement learning doesn't work very, very well for VLAs. So in this case, it's kind of a good match to use like this approach. And I believe it's very, very practical, and I recommend you to try to do something like this when you experiment with reinforcement learning. And finally, the inference-time optimization. I also think it's a nice idea. I don't like to do grid search. I don't like to do like ablation, as you may see in my videos. But this kind of Thompson sampling approach allows to get all this optimization for free. And I think it's very cool. And also, as we already do in reinforcement learning, as we already collecting a lot of rollouts, why don't apply this optimization on top and get even better results? So I think it was a good idea. And try to use it in your projects and let me know if it works for you or not. What I think wasn't so good and probably can be adjusted. So first of all is manual recovery collection, or like dagger collection simulation. I didn't manage to make it work properly. It wasn't so nice, and I wasn't so good at this controlling the robot in simulation and so on. So probably it can be done better. And anyway, we will talk about it in the next video, where I will talk about the second real-life part of the competition, where this kind of human-in-the-loop collection was actually a key part of my solution. Another thing that I didn't fully resolve, and I found it pretty annoying, and there were like a lot of bugs during the development, is that quite often the model actually overfit into some artifacts of the simulation. So it's like very, very tricky to train model in simulation, because it can find some things that doesn't make any sense, but actually just generated by environment, and it's like some just small feature of the simulation, and it completely overfits to this feature. And then this transfer to the real robot doesn't work, or even slight changes in data collection break your pipeline. So, for example, I experimented a lot with video resolution and different codecs that I used to save video, because it was like slowing down the process of rollout collection. And I found that it's very important, even so that we compress the video in the very end to give it to the policy anyway. what we do before is still very important, and sometimes I think that some extra compression or like different codecs, they introduced another artifacts, and I've really seen that model is overfitting into something that I cannot even see as a human, but somehow it finds some patterns, and it was very, very annoying to debug. So there are a lot of these issues in simulations, and I believe that simulations will be better and better. Over time, this sim to real gap will get smaller, and it will kind of become much easier to use. But today, I think it's really, really hard, and you need to pay attention to all these like small annoying things when you train in simulation. Another thing that I still think is a problem is sample efficiency of this approach. I expected it to be more sample efficient when I just started, but eventually, I think in my final training, I have around 12,000 episodes that I collected, and it's not all the episodes. So I collected actually much more. Some of them were like removed over time. So in the very, very end, only like 12,000 left. But it's still a lot. So it's like a huge number of rollouts. It took a lot of time to collect. It took a lot of GPUs to collect. So I believe there should be more optimal ways. And again, probably by tweaking the parameters that I have in my approach, maybe by tweaking this reward function, maybe optimizing something else, we can improve it and make it more sample efficient. I think it should be eventually. Now it feels like a little bit as a problem, and it makes it much harder to train it on the more complex problems. So here, at least our rollouts were like 10, 15 seconds usually, and it's pretty short. So I could collect all these thousands of rollouts, but for the problem that is spanning for like 10 minutes, it's much, much, much harder. Overall, I think there are a lot of space. I think this reinforcement learning for robots, for VLAs and similar models is a bit underdeveloped area, and there should be a lot of easy wins how to optimize it. And I think one of them is about this sample efficiency. If you're doing research in this area, I'm pretty sure it's should be interesting one, and you can make nice improvements and discoveries here. But anyway, we will come back to both these problems in the next video. And again, the reminder that the next video will be about the real life part of the competition. So after this simulation round was over, we had a pretty short period of time to adjust our models to make them actually work in the like real life, in the real setup. And there were a lot of problems, a lot of sim to real gaps, and even like real to real, because we didn't have the access to the original robot that was used to collect data and that was used for the final evaluations. So there were like a lot of problems to solve, a lot of gaps to close, a lot of this recovery behavior to train policy to follow, and so on. And I used pretty different approaches and different methods comparing to the first simulation round. So I think the next video will also have a lot of interesting things to discuss. So if you don't want to miss the next video, please subscribe to this channel, click this bell button, like this video, and ask any questions if you have. I read all the comments, I try to answer your questions, I try to incorporate some of these answers into my following videos. So yeah, don't be shy, please talk to me and ask your questions, and maybe give me some comments or any feedback that you have. And that's it for today. Thank you for watching, and see you in the next video. Bye.